next thing we want to take a look at is the theorem on the number of roots of an nth degree polynomial equation. And we have already mentioned this theorem in some of our previous problems. So let's write that theorem in our notes. Once again, this is the theorem. This is the theorem on the number of roots, right? The theorem on the number of roots or zeros of an nth degree polynomial. Theorem on the number of roots of an nth degree polynomial. This theorem states that every polynomial of degree n greater than or equal to 1 has exactly n roots or zeros. Every polynomial of degree n greater than or equal to 1 has exactly n roots or zeros. Now this, of course, is assuming that we count any double roots twice, any triple roots 3 times, and so forth. So this is if a root of multiplicity k is counted k times. So this is if a root of multiplicity k is counted k times. For example, if I have x squared equals 0, if I have x squared equals 0, I see that my degree here is 2. That's my degree. So that means that I should have 2 roots to this polynomial equation. There should be 2 roots. But if I look at this, if I look at what I have here, the only number that will work in this polynomial equation is 0. X equals 0. It's what we call a double root. Or it's a root or 0 of multiplicity 2. It's a root or 0 of multiplicity 2. So we have to count it twice. That's what that means. We have to count that root twice. So that's why we can still say that this polynomial equation has 2 roots, because we're counting that root twice. Okay, let's look at another example of this theorem. Okay, so this is a VCR tape, so at any time you can stop the tape, rewind it, you can turn it back to something that you didn't understand or something that you didn't get. That's one of the advantages of having this type of instructional process. You can listen to this tape as many times as you want to. You can stop the tape at any time. You can turn the tape back at any time to review something that was said previously. So, for example, an example of this theorem, suppose we have f of x equals x to the 4th plus 10x to the 3rd minus 11 x squared. Suppose we have that polynomial equation, and we want to find the zeros or the roots of that polynomial equation. Keeping in mind here that zeros, roots, x-intercepts, those terms are used interchangeably. So the first thing we do here to find the zeros, which is what we want to do, we have to let the y or f of x be 0. So that means that we get the polynomial equation x to the 4th plus 10x to the 3rd minus 11x squared equals 0. The next thing we want to do is factor this polynomial equation. First of all, we factor out the greatest common factor. The greatest common factor is x squared. When we factor that out, we get x squared plus 10x minus 11. And then after that, we see if we can factor this. And in this case, we can. It's a quadratic trinomial, so when we factor it, we get two binomial factors. When we multiply the first two together, we have to get x squared, so that would be x times x. When we multiply the last two together, we have to get negative 11. But when we multiply the inside two, the outside two, add them together, we have to get positive 10. So in this case, we would have positive 11 minus 1. So there we have the complete factorization of that polynomial function. And now, the next thing we need to do is set each factor equal to 0 and solve. So we get x squared equals 0. And this gives us, this is x squared equals 0. So we see that we have a square here. So this square here means that we have to have two roots. And in the original problem, the degree was 4. So in the original problem, we have to have 4 roots or 4 zeros. So we have to end up with 4 roots or 4 zeros. Here we have x squared, so that means we will have 2 roots here. But the only number that will work here, if we solve this, take the square root of each side, we get x equals plus or minus 0. Of course, 0 is 0, so really we get x equals 0. But since we have a square here, we have to have 2 roots. That means that here 0 is a double root, or it's a root or 0 of multiplicity 2. And then we set the other factors equal to 0. We have x plus 11 equals 0. That gives us x equals negative 11. And then we have x minus 1 equals 0. And that gives us x equals positive 1. So that means that for this polynomial function, the zeros are 0, negative 11, and 1. And we should indicate that 0 is a 0 of multiplicity 2. It's a 0, a double root, or a double 0, 0 of multiplicity 2. So a 0 of a root of multiplicity whatever can be any number. It doesn't have to be, the number doesn't have to be 0. The number can be the number can be any number. It can be 5, 6, 7, 8, 24, whatever. It can be any number as long as it's there are 2 or 3 times or what have you. For example, if I have something like f of x, if I have something like f of x equals x plus 4 squared, if I have that, if I try to find the zeros, I would have x plus 4 squared equals 0. And then if I do it by factoring, this will be x plus 4 times x plus 4 equals 0. And when I set each factor equal to 0, x plus 4 equals 0 gives me x equals, I know I have to have 2 roots here because this is squared. The degree here is 2, so I have to have 2 roots. So here I get x equals negative 4. And on the other side, x plus 4 equals 0. I get x equals negative 4. So that means that my 0 is negative 4. Negative 4 is a root or 0 of multiplicity 2. It's a root or 0 multiplicity 2. So whenever you get an expression like this in your factorization, you'll have a root of multiplicity 2. If I had a 3 here, if this were x plus 4 to the third, then I would have a root of multiplicity 3. If it were x plus 4 to the fourth, I would have a root of multiplicity 4. So that's the when you get double, triple, have you roots. And that is the theorem on the number of roots that an nth degree polynomial function or polynomial equation will have. And this rule should help you to find your roots, because you know how many you're looking for, and that's important. If you know how many roots you're looking for, then of course you will know when you have finished finding all of the roots.